Okay, so as in the last video, we mixed volatile with volatile and then we applied Raoult's law in it and we found the partial vapor pressure, right? By multiplying mole fraction of that component by the pure vapor pressure of that component, right? Initially when we were mixing them together, we didn't mix it yet, but we were mixing it, we were going to mix them together. They had their pure vapor pressures, right? This A1 had its own pure vapor pressure, this B had its own pure vapor pressure. So P naught of A represents pure vapor pressure of A and P naught of B represents pure vapor pressure of B. But after getting them mixed together, now A and B will have their vapor pressures but not their pure vapor pressure. Since now they are mixed with each other, now they'll not have pure vapor pressure. Now they'll have of course vapor pressure but not pure. So PA represents only vapor pressure of A and PB represents vapor pressure of B, right? Here I have written some terminologies too. P naught of A represents pure vapor pressure of A, P naught of B represents pure vapor pressure of B, PA represents vapor pressure of A and PB represents vapor pressure of B. Then we applied Raoult's law in it. What does Raoult's law say? In a solution, the vapor pressure of each component is directly proportional to the mole fraction of that component. For example, in a solution, this is the solution, right? Since solute and solvent both are mixed together, and the mixture of solute and solvent is what we call the solution, right? So in a solution, the mole fraction of each component is directly proportional to the vapor pressure of it, or the vapor pressure of each component is directly proportional to the mole fraction of it. If I do talk about this A1 here, right? So the vapor pressure of A is directly proportional to the mole fraction of that component, which means mole fraction of A, right? And the vapor pressure of B is directly proportional to the mole fraction of B, right? So when we remove these proportionality sign, we get is equal to and constant. So PA is equal to, here the constant we get is P naught of A, which is pure vapor pressure of A into mole fraction of A. Same, PB is equal to constant P naught of B, which is pure vapor pressure of B into mole fraction of B. This is how we applied Raoult's law. And then we applied the John Dalton's law to actually get the total vapor pressure of the container, right? Initially we found their partial vapor pressures. We found actually their vapor pressure, but we will gonna call them as partial vapor pressure since they were mixed with each other. That's why we are calling them as partial vapor pressure, not as vapor pressure. Pure vapor pressure we called them since they were alonely, right? But now they aren't alonely, they are in a container with each other. So that's why now we have to call them as partial vapor pressure. So now total vapor pressure of any container can be get by addition of the partial vapor pressure of the components present in that container, right? So this is what we applied here, the John Dalton's law. If we need to find the total vapor pressure of any component, we need to find initially the partial vapor pressure of that component in the container, and then we need to add them together in order to get the total vapor pressure of the container. In today's video, now we are going to mix volatile with non-volatile substance, right? So as this container shows, this is actually what, this is volatile since this has capability to make the vapor pressure, right? So this is volatile. We are gonna mix them together with non-volatile, right? Here we'll have non-volatile wheat. And non-volatile are those which don't have capability to make the vapor pressure. So here we have got non-volatile, right? So they don't have capability to get to make vapor pressure, right? So this is non-volatile. Now for suppose these molecules were A molecules, A, and they don't have capability to make the vapor pressure, right? They are A molecules. We made them mix together with B molecule which have capability to make the vapor pressure. When we mixed them together, right? These were A for suppose, or these were B, since B have the capability to get evaporated or to make the vapor pressure. This is B and this is A, which actually is taking place. See, it is reducing the surface area. If these molecules, the A molecules would not have come here, all the molecules of B would have been evaporated to make the vapor pressure, right? But because of the presence of the A molecules, which are actually non-volatile, they are reducing the vapor pressure, right? So what are they doing? The molecules of A are reducing the vapor pressure. So whenever we mix volatile with non-volatile, the vapor pressure is reduced. When we mix volatile with volatile, the vapor pressure is increased. But when we mix non-volatile with volatile, the vapor pressure is reduced, since the non-volatile molecules take the place of the volatile substances, and when they take the surface, or when they take the place of them, they reduce the surface area, and if they have reduced the surface area, the volatile molecules would not get place to make the vapor pressure or to get up for making the vapor pressure, since vapor pressure is called a vapor pressure just above the liquid surface, right? So whenever it will not go up to the surface area, how will they create the vapor pressure? So that's why when we mix volatile with non-volatile, they actually reduce. The vapor pressure is reduced, and we mix volatile with volatile, the vapor pressure is increased. So this was all for today. From the next video, we're gonna start studying about ideal solution and non-ideal solution.